Actually, this chapter also has something called as methods of differentiation, right? We can pick up in the next class. Possibly this class wouldn't have
No,
that
I
much
don't
time.
think we need to take that up.
Okay, we don't. Okay,
Yeah.
okay. So LHD move to differentiability. So dy by dx is actually the slope of tangent of the curve. Actually, this chapter also has something called as methods of differentiation, right? We can pick up in the next class. Possibly this class wouldn't have
No,
that
I
much
don't
time.
think we need to take that up.
Okay, we don't. Okay,
Yeah.
okay. So LHD is actually f of a minus h minus f of a upon minus h.
I think we
RHD
can
is
just take like integrals up instead.
okay. Not even area of sorry. What is that? Application of derivatives.
I mean, I think we can do that later because I have case and I wanted to do like integrals once.
Okay. Okay. So if they are finite and equal, that means they're differentiable. Okay. Now, reasons for non-differentiability can be reasons for non-differentiability. We saw the reasons for discontinuity. Now, for non-differentiability, we have that the function is discontinuous. See, if a function is continuous, then it may not be differentiable. But if a function is differentiable, then it is definitely discontinuous. Sorry, then it is definitely continuous, right? So if a function is discontinuous, so definitely it would never be differentiable, right? So discontinuity is one of the reasons. Another reason is there is sharp corner in the graph. Sharp corner in the graph. For example, as seen in cases of mod x. The graph of mod x is something like this. Can you see a sharp corner here?
Yeah.
Okay. Actually, you know what sharp corner means? That you are having two slopes at this point. Now, at a particular point, you cannot have two slopes. This is similar to what you study in magnetic fields, right? At a particular point, there cannot be two directions of magnetic field. There also, we take the idea of slope only. Okay. Then vertical tangent in the graph. Vertical tangent in the graph. For example, as seen in the case of this thing. Now, very obviously, this and this are actually inverse of each other. So that means they are mirror images of each other about y equals to x. Y equals to x is something like this. Y equals to x cubed. Now tell me one thing. For x between 0 and 1, which will be greater, x cube or x 1 by 3? Common sense. Very important concept.
Yeah.
Which will be greater?
X cube and x 1 to the power 3, right?
Yeah. Which will be greater between 0 and 1?
1 second. X cube will be greater. I mean, at x to the x is 1, then both are same only, right?
No, I'm asking about between 0 and when 0 and 1 are not included. Strictly between.
X 1 by 3.
Yes. So I'll make x1 by 3 as like this and x cube as this. Now after 1, what happens? And they're all equal at 1. So let's intersect them. After 1, what happens is x cube rises up and this goes down. Right. Similarly, for the negatives, can you tell me? So obviously it would be symmetric, like so, like
Yeah.
okay. Um. Okay. Some like this. Okay. So this is x1 by 3. This is x cube. Um. So in the graph of x1 by 3, can you see? Okay, not made properly. Can you see how there's a kind of a vertical tangent at x equals to 0? You know what that means? That this function is not differentiable at x equals to 0. You can try it yourself. Differentiate this function. What are you getting? Are you getting 1 by 3 x 1 by 3 minus 1, which is 1 by 3? Is this 1 by x 2 by 3? Is this differentiable at x equals to 0? Can you put x equals to 0 here?
No.
Yeah, that means this function is non-differentiable at x equals 0. Is there any other point where it's not differentiable?
No, I think, yeah, that's it.
Yeah, because that is the only point. See, graphs gives us confidence, right? You can see how there's only vertical tangent at x equals to 0. Otherwise, it's all continuous differentiable everywhere. It's continuous at x equals to 0 as well, but because it is having a vertical tangent, so it's non-differentiable. Okay. Now, algebra of differentiable functions, again very important. Algebra. Let's say f g f plus minus g f into g f by g f of g. So differentiable, given that g of x should not be equal to 0. And again, same case, differentiable. Non-differentiable cannot say, non-differentiable cannot say, and non-differentiable cannot say. Okay. I can, take an example for this. Maybe you're, if you're getting confused, where do we use this? Find the number of points of non-differentiability of cos mod x plus x power 1 by 3. See, you would probably be confused how to even proceed. That is where algebra comes into play. Can you see how this is kind of a bait function? Because cos x something looks like this? No. Cos x looks like this. Okay.
Yeah.
Cos x is an even function. So you put x or you put minus x, you're going to get the same output only. So that means this mod is not required. So that means this is same as writing just cos x.
Mm-hmm.
Or definitely you can make the graph for cos mod x also. And there you will see that, oh, you're having nothing wrong there. I mean, no, none of these reasons, none of these reasons. Okay. So cos x becomes a differentiable function, and this is a non-differentiable function at x equals to 0. Differentiable plus non-differentiable gives me what? Non-differentiable. So can you tell me what is the point of non-differentiability of this function? X equals to 0. That's the only point. When
Yeah.
x is not equal to 0, when x is not equal to 0, this is differentiable. This also becomes differentiable. Differentiable plus differentiable. So that is the only point.
Mm-hmm.
Make use of that. Okay. Now, let's say you have to check for differentiability. 3 steps. First step, check for continuity. In a lot of questions, they will not say that if it's a continuous function, right? You properly check if it is continuous. If it is not continuous, then you can straight away say that is a non-differentiable. Make sense?
Yeah.
Okay. Another step, use LHD and RHD. Another step, shorter method. Now, actually, you might have also experienced this yourself in this chapter. Sometimes, this you see the solutions they're using LHD, RHD. Sometimes they're not. Sometimes they're just differentiating it. What is the difference? So, very important difference. A very, 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 very important question. Like it literally came in. Like it came in 225 G advanced, uh, where they tested this idea only. So we'll talk about that. So actually the thing is, you should use this for complex looking, lengthy looking, weird looking piecewise functions. When you have a lot of functions, ex, sin x, they also put this thing, everything they put, right? Generally for exponential and everything, I'll say use this only. Otherwise for this, what's the method when you can use this? So let's say you are having this function. Let's say x plus 2, x plus 3. Okay. Tell me one thing. This function we define for x greater than equal to 0. This we define for x less than 0. If I ask you f of 0, what is that?
2.
Okay, wait. Okay, now tell me.
Fx equal to x plus 2x when x is greater than equal to 0, and then x plus 3x when x is less than equal to 0. So it's till then it's 0.
Correct. Tell me one thing. We are defining for x equals to 0. For you made use of this branch, right? But if you would have made use of this branch, would the answer differ?
No.
Yeah, that means this is interchangeable, or you can swap it. That
Yeah.
is the case when you can just simply differentiate, right? Let's see. This function is it continuous function? Yes, it is. We are getting continuous. Correct. So good. Okay. Now let's check for differentiability. Now you can use a shorter method because of this logic that I told you. So f dash x 3, 4, and when we are checking for differentiable, we don't talk about points. We talk about pure intervals only. Do you think these are differentiable? Is this equal to this?
No.
No. That means it is non-differentiable. Another way out, just make the graph for it. This is what? 3x? 3x is something like, let's say, this. This is 4x. How would it be like? Tell me.
The slope would be just the slope would be greater.
Yeah, so basically, let's say my 3x is coming out to be this here. So my 4x would be like this. So there's a sharp turn here actually. Like, it does not look that sharp, but it is a sharp turn.
Yeah.
Like something like this is forming. Okay. Okay. Okay, now one more very important concept actually, which is like this also applies in continuity, by the way. Let's say differentiability in open interval, in a closed interval. See, tell me one thing here. Let's say you're
Many students practice maths regularly, but still don't improve. Because the same mistakes keep repeating, and no one tracks them. In exams, this turns into confusion and blank moments. With one-to-one mentoring, every mistake is corrected, and real improvement begins.